Okay, in this lesson we're going to continue to look at optimization problems. In the last lesson we looked at a problem where we weren't dealing with a word problem, we were dealing with just a mathematical problem. We were setting up a solution region given constraints and then investigating the objective function to find out our maximum and minimums. In the next problem we're going to look at a word problem. The nice thing about word problems is sometimes you can actually figure out the answer without even setting up the system. In this case that may be true in some cases, however, we want to try and set up the solution region and investigate it that way. But it is useful to kind of investigate the system as is without the solution region. So here's the problem that a construction company has. A construction company is competing for a contract to build a fence. The fence will be no longer than 50 yards and will consist of narrow boards that are 6 inches wide and wide boards that are 8 inches wide. So you've got to picture the two types of boards that they're going to use here. I'm going to suggest that that's our first constraint. It's no longer than 50 yards and will consist of narrow boards that are 6 inches wide and wide boards that are 8 inches wide. We'll deal with that in a second. That's a constraint. Second constraint is that there must be no fewer than 100 wide boards, so they have to have at least 100 wide boards and no more than 80. So they can have no more than 80 narrow boards. So those are their constraints. And then we're looking at cost here. The narrow boards cost $3.56 each, and the wide boards cost $4.36 each. And the question says, determine the maximum and minimum cost for the lumber to build the fence. So we want to find out, this is our objective. Maybe I'll just circle it. This is our objective. They want to find out what's the most expensive our fence could be, and what's the least expensive our fence could be. Well, if you read the problem carefully, that it wants to be no longer than 50 yards and there's no fewer than 100 wide boards and no more than 80 narrow boards, you might assume that the cheapest, and this would be correct, but we'll find that out as we go, you might assume that the cheapest fence that they could build would be with just 100 wide boards, because that would be less than 50 yards and that would be no more than 80 narrow boards. It would be 0 narrow boards. So 100 wide boards would be their cheapest fence. And that would just be 100 wide boards times $4.36. So that's going to be $436. But in saying that, we like to investigate this using the solution region, but that's kind of the idea. What's their most expensive and cheapest fence we could do? We're going to solve this mathematically. So let me start with the two easier constraints. Let's start with no fewer than 100 wide boards. So I've done some of the work in advance. We're going to call n the number of narrow boards they can use and w the number of wide boards. And I've also extended, if you're using my study guide, you might want to pause this at this point in time, start writing some notes in, as well as I've extended the vertical axis to go up by 20s up to 300, and the horizontal axis to go up by 20s up to 240. You'll find out why in a little bit. This is our wide board axis, this is our narrow board axis. So you may want to pause it and start filling out your study guide right now, and you could also, if you want to, try some of the constraints, but I'm going to start working on that right now. So no fewer than 100 wide boards. That would be this right here, that wide boards have to be more than or equal to 100. And if I was to draw that constraint, the boundary would be where wide boards is exactly 100. So boundary is where wide is exactly 100, and wide is exactly 100 right here. And if it's more than, it's no fewer than 100, it's actually going to be this region here. They're allowed to have more than 100. They're not allowed to have any fewer than 100. So that's that constraint here. The next constraint was no more than 80 narrow boards. So that would look like this, that the narrow boards have to be less than or equal to 80. Your boundary for that particular constraint would be where n is equal to 80. So n is equal to 80 here. So here would be your boundary line, and if you're not allowed any more, that would be below 80. So there's our start. The more difficult of these constraints has to do with the cost, the length of the fence. It said the fence is no longer than 50 yards. So first of all, we're dealing with inches regarding the boards, but yards regarding the length of the fence. So we have to make these common. So we must know that 1 yard is equivalent to 36 inches. So if I wanted to find out 50 yards, if I wanted to know what 50 yards was, I would do 50 times 36. That would be 1,800 inches. So we know that 50 yards is equivalent to 1,800 inches. So that's as long as our fence could be. So it has to be less than or equal to 1,800 inches. Now what has to be less than or equal to 1,800 inches? Well, the length of the fence. And the length of the fence is 6 inches per narrow board plus 8 inches per wide board. It's a little bit more difficult. This has to do with the length. 6 inches per narrow board plus 8 inches per wide board has to be less than or equal to 1800 inches. To find out your boundary, since it has two variables, we can find the two intercepts. I would think the easiest way, and you may want to go way back to 6.1 if you don't know how to find the boundary lines. There's lots of lessons there. If I put in n equals 0, I would have 8w equals 1800, and I'd divide by 8, and I would get that w is equivalent to 1800 divided by 8, and that gives me 225. So the wide board intercept is 225, so roughly right here. Okay, and if I substituted w equals 0, I would have 6n equals 1800, and if I divide by 6, I will get that n is equal to 300. So the narrow board intercept is 300. So we've got our boundary line. Our boundary line is between those two intercepts, so it looks roughly like this. And the question, or sorry, the inequality states this, that it has to be less than or equal to 1800 inches. So that would be below that line. That line represents where the fence would be exactly 1800 inches. So less than would be all these combinations here. So finally, given our constraints, I think you can see where our solution region is. Our solution region is this one right here that I'm outlining in black at the moment. That's where all three overlap. So the last thing we need to do is define what these corners are, what the coordinates of those corners are. And the corners appear to be the following. Let me label them. This point here would be 100 wide and 80 narrow boards. This point here would be 100 wide and no narrow boards. And as I said at the very beginning of this problem, that's going to be our cheapest fence, 100 wide boards and no narrow boards. This point right here is going to be 160 wide boards and 80 narrow boards, and this point right here is 225 wide boards and 0 narrow boards. So those are the corners of my solution region. Why is that important? Well, if we're asked to determine the maximum and minimum costs for the lumber, it's going to be occurring in those corners. So first thing we need to do is figure out our objective function. So if our objective is to maximize and minimize the cost, what is, and you can see this here, what is our objective function? Well, it would be the cost. And cost is equivalent to, we have the cost, $3.56 per narrow board, so $3.56 per narrow board, plus $4.36 per wide board. So that would be our cost. Now, which would be the cheapest? We actually already know that. It would be cheapest to have the least of both types. So the least of both types is going to be this point right here. So we know that the minimum, you could test all the points, but the minimum cost would be where we have exactly no narrow boards, so it would be 356 times 0 plus 436 times 100 wide boards. That's going to give us a cost of $436. So the minimum cost would be $436, and that would be at the point 100 wide boards and 0 narrow boards. Okay. Now the maximum cost, if you look at it, what's going to be more expensive, this point or this point? Would it be more expensive to have 100 wides and 80 narrows, or 160 wides or 80 narrows? Well, definitely this one. So you can assume that this point is not a maximum or a minimum. However, it might be a little bit more difficult. You may actually have to calculate them to know which one of these is more expensive, 160 wides or 80 narrows, or 225 wide boards and 0 narrows. So let's investigate that really quickly. The maximum could either be one of the following. Let's check 160 wides and 80 narrows. So that would be 356 times 80 plus 436 times 160, and that's going to give us, let me just do this in one step, but you want to be careful to use your brackets. So 356 times 80 plus 436 times 160. That would be a cost of $982.40. Let's find out the cost of 225 wide boards. Well, that cost would be $4.36 times 225. because there's no narrow boards. So 436 times 225 wide boards is $981, which is cheaper. So if you look at these two costs, the more expensive cost is that one right there. So that would be $982.40. And that would be at the point where we have 160 wide boards and 80 narrow boards. And that is that particular type of problem.